Hey folks, just looking at another problem related to how acids will increase the solubility of these slightly soluble compounds. So here we're looking at acetic acid. Now remember that is weak. Its chemical formula, as you certainly know, is is HC2H3O2. So it's an organic weak acid. An alternate way to write its formula, which is probably more accurate, is CH3COOH. This carboxylic acid group is what indicates it's acidic. And the bottom line is organic oxy acids are weak. Doesn't ionize 100%. So that's going to change the approach here a bit. We're not going to ionize the acid. We're not going to ignore the anion and cancel it out as a spectator. So anyway, the acetic acid is going to end up reacting with those two hydroxide ions. So if I react those, now in order to completely react to those two hydroxide ions, I'm going to need two acetic acid molecules. Now when this reaction occurs, what will end up happening is the acid will donate its proton to the base, the hydroxides, and so we'll end up forming acetate, two of them, end up forming two acetates, and will form, notice, two water molecules. But this reaction also is going to have a somewhat low K value. I don't really know. We could look it up if it were really important. And so, however, being that these acid molecules are reacting with those hydroxides, we'll end up forming magnesium hydroxide plus acetic acid, two of them. The two hydroxides will cancel, and we'll be left with forming magnesium ion, the acetate ion, and then a pair of water two acetates, plus a pair of water molecules. The overall K of this reaction, since we'd multiply those two together, the overall K has got to be less than 1, just to remind you of that fact. If we then look at the calcium carbonate in vinegar, so I bet a bunch of you did this as kids in your elementary days, maybe middle school days. Maybe you did something where you took baking soda and poured vinegar on it, something along those lines. This would be a similar reaction, except we're looking at calcium carbonate, again, which is not a fully soluble compound. So the first reaction that's got to happen, much like we did before with the calcium carbonate and hydrochloric acid, the calcium carbonate will begin to dissolve, but only slightly. The K value of that reaction is slight, and so that K value is less than 1. Same deal here. And so as the acid is added, we're going to need two acetic acid molecules to react with that carbonate ion. And what we'll end up forming is the acetate ion, both of them, and the two hydrogen ions will be donated to the carbonate, which will end up forming H2CO3. But as I pointed out in example number 2 or 3 on the previous page, the carbonic acid will decompose into water and carbon dioxide gas, in which case you'll get this bubbling reaction. Again, the K of this is going to be somewhat low, but as that acid, and I could say the same thing for both of these reactions, the added acid causes, as it removes hydroxides, it causes system number 1 to shift to the right. So both the first example on page 8 and the second example on page 8 are causing these systems to shift right. So the reduces the hydroxide, this reduces the carbonate, so that virtually the same kinds of things can be said here. You lower the carbonate concentration, and the system shifts to the right. System number 1 shifts to the right. So I'll leave you to that. I'll let you practice some of those problems, take a break, get something to drink, come on back, and we'll talk about page 8, and we'll get more into these buffers and titrations and such.